When looking at the night sky, humans have always been trying to figure out, how did all this begin? From ancient stories passed down through generations to the groundbreaking discoveries of modern science, we've been driven by a need to understand where it all came from. Today, science has brought us closer than ever to answers, and the Big Bang Theory is the leading explanation of how our universe began. It tells us that about 13.8 billion years ago, everything we see now started as a tiny, unimaginably hot and dense point, a singularity. From there, the universe began expanding, with time, space, and everything else spreading out and evolving into the vast cosmos we know today. The story of the Big Bang is as fascinating as it is humbling. At first, the universe was so dense and fiery that nothing like the stars, planets, or life we know could exist. Then, in a split second known as inflation, it expanded incredibly fast. This cosmic growth spurt set the stage for everything that came after. As the universe cooled, the first building blocks of matter, like quarks and electrons, came into existence. These particles later combined to form atoms, and about 380,000 years after the Big Bang, the universe became transparent, allowing light to travel freely for the first time. This light still lingers today as a faint glow called cosmic microwave background radiation, a whisper from those early moments. The journey to understanding this theory has been remarkable. In the 1920s, Edwin Hubble made a groundbreaking discovery that distant galaxies are moving away from us, which technically means that the universe is expanding. This was the first strong evidence that the cosmos had a beginning. Then, in 1964, two scientists stumbled upon the cosmic microwave background radiation while working on a radio antenna, giving us further proof of the Big Bang. Together, these findings changed how we see the universe, bringing the Big Bang Theory to the forefront of scientific thought. Even so, the story doesn't end there. Over the years, other theories have challenged or added to our understanding. The steady-state theory explains that the universe had no beginning or end, with matter constantly appearing to keep things balanced. But the discovery of the cosmic microwave background radiation proved otherwise. Other ideas, like the cyclic universe model and the multiverse hypothesis, offer their own twists, hinting at endless cycles of expansion and contraction, or the possibility that our universe is just one among many. These ideas push us to think even bigger, sparking curiosity about the infinite possibilities of existence. The cosmic microwave background radiation remains one of the most incredible pieces of evidence we have. It's like a snapshot of the universe as a baby, a faint glow filled with tiny ripples that reveal how galaxies and stars eventually formed. Over the years, scientists have used advanced technology to study this radiation in incredible detail, unlocking secrets about the universe's birth and early growth. The idea of a beginning to everything raises some of life's deepest questions. For centuries, philosophers and religious thinkers have debated whether the universe had a starting point or has always existed. The Big Bang aligns in some ways with ancient creation stories, suggesting a moment when everything came into being. But it also leaves us with profound mysteries. If the universe had a beginning, what caused it? What existed before it? These questions invite us to reflect on the nature of time, existence, and our place in the cosmos, connecting the realms of science and philosophy in meaningful ways. Edwin Hubble's discovery of galaxy redshifts wasn't just a scientific breakthrough, it was a revelation. It showed us that the universe is alive, dynamic, and constantly evolving. His work laid the foundation for everything we know about the cosmos today, and his legacy continues to inspire scientists and dreamers alike. Despite how far we've come, so much about the universe remains a mystery. Dark matter and dark energy, which make up most of the cosmos, are still puzzles we haven't solved. And the question of what came before the Big Bang, if anything, keeps scientists exploring bold new ideas like string cosmology and loop quantum gravity. The possibility of a multiverse adds yet another layer of wonder, suggesting that our universe may be one of countless others. These unanswered questions remind us that the universe is vast, and there's always more to discover. The story of the Big Bang is more than just a tale about the cosmos. It's a reflection of us. It's about our drive to ask big questions, our determination to seek the truth, and our endless capacity to wonder. The more we learn about the universe, the more we understand about ourselves and our place in this ever-expanding story. And as we continue to explore, one thing becomes clear. The quest for knowledge is as infinite as the cosmos itself. Time is something we all live with every moment of our lives. It shapes how we experience everything, yet it's hard to pin down what time really is. Is it like a river flowing constantly? Or is it something we've created to make sense of the world? Do the past, present, and future all exist at once? Or is time just a way to measure how things change around us? These are questions that have puzzled people for centuries. When we ask, what is time? We often think of it as the way events move from yesterday to today and into tomorrow. Time feels invisible, yet it's what keeps the universe running in order. Scientists say it's a dimension like space that forms the fabric of space-time. But philosophers have long wondered, is time real or is it something we've imagined? Centuries ago, Isaac Newton described time as absolute, like a giant invisible clock ticking away, independent of everything else. Then Albert Einstein turned that idea on its head. In his theory of relativity, Einstein showed that time is not fixed. It changes depending on how fast you're moving or how strong gravity is. Time became part of space-time, bending and stretching with the universe. For us, time feels personal. We experience it through our memories of the past and our hopes for the future. Our brains work hard to create a sense of now, pulling together moments so we can make sense of them. Around the world, people think about time differently. In Western cultures, time is often seen as a straight line. Things happen in order from beginning to end. This way of thinking shapes how we write history and understand life. But in many Eastern traditions, like Hinduism and Buddhism, time is seen as a circle. Life, death, and rebirth happen again and again like the cycles of nature. Indigenous cultures often view time as a relationship tied to the rhythms of the earth and the stars. These perspectives remind us that time is not just one thing. It's many things depending on how we look at it. Einstein's work gave us amazing insights into how time behaves. In 1905, he showed that time can slow down for objects moving very fast, a concept called time dilation. For example, astronauts on high-speed space missions would experience time more slowly than people on Earth. Later, in 1915, Einstein explained how gravity affects time. Near massive objects like planets or black holes, time moves more slowly. Even on Earth, time passes slightly faster at the top of a mountain than at sea level. We see this effect every day in GPS satellites, which need to account for time running differently in space. At the smallest scales, quantum physics changes the game. The strange world of particles doesn't always follow the rules we're used to. Time in quantum systems isn't so clear. It doesn't always move forward in the way we expect. Particles can even seem to affect each other instantly across great distances, a phenomenon called entanglement. This makes scientists wonder, could time itself be something that emerges from deeper processes we don't fully understand yet? For centuries, philosophers have explored whether time is real or just something we use to organize life. Some, like Immanuel Kant, believed time is a tool our minds use to make sense of reality, not something that exists on its own. Others talk about the arrow of time, the idea that time moves in one direction, from past to future, driven by the universe's natural tendency toward chaos or entropy. Time also raises big questions about free will. If the future is already shaped by the past, do we really make our own choices? Or are we just following a path that's already set? These questions remind us how mysterious time really is. Time is more than just a scientific puzzle. It's a part of who we are. It challenges us to think about life, existence, and the universe in deeper ways. Whether we're studying Einstein's theories, exploring quantum mysteries, or pondering life's big questions, time keeps us curious. It's a journey we're all on together, and it pushes us to keep searching for the truth about the world and our place in it. Consciousness is one of life's greatest mysteries, something so central to who we are yet so hard to define. For thousands of years, people have wondered about what it means to be aware of ourselves, our emotions, and the world around us. From ancient philosophers in Greece to today's neuroscientists, the question of consciousness has captured human imagination. Is it simply something the brain creates, or does it exist beyond our physical selves? How do our personal experiences, our happiest memories, deepest fears, and everyday thoughts come from the biological processes inside our heads. At its heart, consciousness is the state of being aware, of knowing that we exist and experiencing the world as it happens. It's the thread that ties together our memories of the past, our presence in the now, and our dreams for the future. But trying to explain consciousness is no easy task. Scientists and philosophers have come up with definitions and theories, but none fully capture the mystery of what it is or how it works. Consciousness is often described in two parts. First, there's phenomenal consciousness, the deeply personal experience of being alive. It's what it feels like to taste your favorite dessert, to hear a song that moves you, or to fall in love. Then there's access consciousness, which is about how we process information to make decisions, reason, and act. Together, these two parts help shape our awareness. But there's still so much we don't understand. Throughout history, people have tried to explain consciousness in different ways. Ancient thinkers like Plato and Aristotle saw it as part of the soul, tied to our ability to think and make moral choices. Later, René Descartes argued for dualism, the idea that the mind and body are separate, with the mind existing beyond the physical world. Today, we explore consciousness not just through philosophy, but also with psychology, neuroscience, and even artificial intelligence. One reason consciousness is so hard to understand is that it's deeply personal and subjective. It's not like a physical object we can measure or see. It's something we feel and live, which makes it difficult to study in clear, objective ways. There are three big theories about consciousness that people have debated for centuries: dualism, materialism, and panpsychism. Dualism, made famous by Descartes, says the mind and body are separate. The mind controls our thoughts and experiences, while the body exists in the physical world. This theory respects the unique, non-physical aspects of our inner lives, but it struggles to explain how something immaterial, like the mind, can interact with something physical, like the brain. Materialism takes the opposite view. It argues that consciousness comes entirely from physical processes in the brain. This idea fits well with discoveries in neuroscience, which show clear links between brain activity and how we experience the world. But materialism leaves a big question unanswered. How do physical processes create something as rich and personal as subjective experience? Panpsychism offers a different perspective, suggesting that consciousness might be a fundamental part of the universe, present even in tiny particles. This theory offers a bold way to explain how consciousness might arise, but it's hard to test scientifically, which makes many people skeptical. Modern science has made incredible progress in studying consciousness. Using tools like brain mapping and experimental techniques, researchers are uncovering how our awareness works. For example, scientists have found that parts of the brain like the prefrontal cortex and thalamus play a big role in creating our sense of self and helping us make decisions. But even with these discoveries, mapping out consciousness completely remains an enormous challenge. One breakthrough concept is the neural correlates of consciousness, the brain processes that are essential for being aware. Instead of coming from just one spot in the brain, consciousness seems to arise from networks of neurons working together. Sleep studies have also provided valuable insights. In REM sleep, where vivid dreams occur, our minds create rich imaginary worlds, even though we're unconscious. Studying patients with conditions like comas or locked-in syndrome, where people are conscious but unable to move or communicate, helps scientists understand the delicate boundaries between awareness and unconsciousness. But what about machines? Could they ever become conscious? This question bridges science and philosophy. While artificial intelligence can perform impressive tasks like recognizing faces or holding conversations, these systems aren't truly aware. They don't feel. Some researchers hope to build machines that could one day achieve consciousness, but we're not there yet. If it ever happens, it would raise huge ethical questions. Would conscious machines have rights? How would we define personhood for something non-human? One of the biggest questions about consciousness is what philosopher David Chalmers called the hard problem. This asks, how and why do physical processes in the brain create subjective experiences? For example, why does seeing the color red feel the way it does to you? Science can explain how the brain processes color, but not why it feels like something to see. Some believe solving this mystery might require entirely new ways of thinking. In the meantime, practical research continues to unlock more about consciousness. Techniques like brain stimulation are helping scientists explore how our minds work and even alter how we perceive reality. Consciousness isn't just a scientific puzzle, it's deeply tied to how we see ourselves and the world. It makes us wonder, do we really have free will, or are all our actions predetermined by our brains? Is consciousness just a product of biology, or is it something greater? These questions remind us that understanding consciousness isn't just about the brain. It's about understanding life itself. With every discovery, we take a step closer to unraveling the mystery, but the journey is far from over. Whether through science, philosophy, or exploring the edges of technology, the quest to understand consciousness will always inspire and challenge us. The origin of life on Earth is one of the most fascinating and mysterious questions that has captivated humans for centuries. How did simple, lifeless molecules come together to form the complex organisms capable of reproduction, evolution, and adaptation? This question has led people to search for answers in many fields, from biology and chemistry to astronomy and philosophy. The quest to understand life's beginnings is not just a scientific endeavor, but also a deeply emotional one, as it connects us to our very existence and our place in the universe. Over the years, numerous theories have been proposed to explain how life might have started. Some of these ideas are rooted in ancient myths, while others come from modern scientific thinking. The most well-known scientific theories include the primordial soup hypothesis, panspermia, and the hydrothermal vent theory. Each of these offers a different perspective on where and how life began, giving us a glimpse into the vast possibilities that lie ahead. However, before we dive into these theories, it's important to ask, what does it truly mean for life to begin? Life, in its simplest form, has three key characteristics: metabolism, reproduction, and adaptation. Metabolism is the ability to use energy from the surroundings, reproduction allows life to make new life, and adaptation enables organisms to change and evolve over time. The first life forms on Earth were likely very simple, single-celled organisms that eventually gave rise to the incredible diversity of life we see today. Around 4.5 billion years ago, Earth was a hot, molten ball of rock. Over time, it cooled and formed a thin crust, with volcanic activity, lightning, and meteor impacts shaping the young planet. The atmosphere was vastly different from what we breathe today, filled with methane, ammonia, hydrogen, and water vapor. These harsh conditions, however, created the perfect environment for life to take root. One of the most famous theories about the origin of life is the primordial soup hypothesis. According to this idea, life began in the early oceans of Earth, where simple organic molecules mixed together in a soup of chemicals. Lightning, ultraviolet radiation, and volcanic activity provided the energy needed to trigger chemical reactions that formed more complex molecules. These molecules then gathered in the oceans, creating the building blocks for life. While this theory is compelling because it shows how basic molecules could form naturally, it doesn't fully explain how these molecules turned into self-replicating systems, which is crucial for life to begin. In 1953, Stanley Miller and Harold Urey conducted a groundbreaking experiment to test the primordial soup hypothesis. They recreated the conditions of early Earth in the lab using gases like methane, ammonia, and hydrogen to simulate the atmosphere, electric sparks to mimic lightning, and heated water to represent the oceans. After a week, they found that amino acids, essential building blocks of life, had formed. This discovery was a major breakthrough, providing evidence that life's basic components could arise through natural processes. However, while their experiment showed that amino acids could form, it didn't explain how these molecules could evolve into complex proteins, or how DNA and RNA came into existence. Another theory, known as panspermia, suggests that life, or at least its building blocks, might have come from space. The idea is that organic molecules like amino acids have been found in meteorites and comets, suggesting that life's building blocks could exist elsewhere in the universe. Some scientists even believe that microscopic life could have survived the harsh conditions of space and been carried to Earth on meteorites. There's evidence supporting this theory, like the discovery of amino acids in space rocks and the existence of extremophiles, organisms that thrive in extreme environments on Earth. This suggests that life could exist in many different places across the universe. But if life did come from space, the question remains, where did it originally begin? Panspermia doesn't provide a final answer. It simply shifts the mystery elsewhere. The hydrothermal vent theory offers another intriguing possibility, suggesting that life may have originated deep in the ocean, near hot, mineral-rich vents on the seafloor. These vents, which release heated water from beneath Earth's crust, create a unique environment full of energy and nutrients. Some microorganisms, known as extremophiles, thrive in environments similar to hydrothermal vents, hinting that early life might have done the same. Laboratory experiments simulating vent conditions have successfully created organic molecules, providing additional support for this idea. Yet, The extreme heat and pressures near the vents could potentially destroy organic molecules, making it unclear whether these vents could truly be the birthplace of life. Despite these theories, scientists face significant challenges in replicating the exact conditions that led to life's emergence. Life is incredibly complex, with many systems, like the genetic code, metabolism, and cell membranes working together. Creating these systems in a laboratory is a monumental task. One theory, the RNA world hypothesis, suggests that RNA could have been the first molecule to store genetic information and catalyze chemical reactions. However, creating self-replicating RNA molecules in the lab remains a major obstacle for scientists. Furthermore, the role of chance in the origin of life cannot be overlooked. The right conditions and random occurrences might have made life's emergence an incredibly rare event, adding another layer of mystery to this already complex puzzle. The origin of life remains one of science's greatest challenges, but it is also a source of hope and excitement. Theories like primordial soup, panspermia, and hydrothermal vents offer valuable insights, and experiments like the Miller-Urey study have shown us that life's building blocks can arise through natural processes. Yet many questions remain unanswered, leaving the story of life's beginnings still unfolding. This quest to understand where we came from is not just about science. It's about our deep desire to understand who we are and how we fit into the vast, mysterious universe around us. As we continue to explore and experiment, we move closer to answering one of humanity's most profound and emotional questions. How did life begin? The question, are we alone in the universe, has captured human imagination for centuries. Ancient civilizations pondered the existence of celestial beings, while modern science continues to push the boundaries of our understanding of life beyond Earth. Are there intelligent civilizations somewhere in the vast expanse of the cosmos? How can we find them? These questions have driven researchers, philosophers, and astronomers to develop tools, theories, and missions dedicated to uncovering the truth. SETI, or the Search for Extraterrestrial Intelligence, is the ongoing effort to detect signals or signs of intelligent life beyond Earth. Although it might sound like something out of science fiction, SETI is based on solid scientific methods and uses advanced technology. The idea of trying to contact extraterrestrial civilizations dates back to the 19th century. In 1896, Nikola Tesla claimed that his wireless technology could be used to detect communications from Mars. The modern foundation of SETI began in the 1960s, when astronomer Frank Drake conducted one of the first radio signal searches under Project Ozma. Then, in 1984, the SETI Institute was established, becoming a global leader in the scientific study of life beyond Earth. SETI uses powerful tools like radio telescopes, such as the Allen Telescope Array, to scan the skies for signals from intelligent civilizations. It focuses on narrow bandwidth radio signals which don't occur naturally. There is also optical SETI, which searches for laser pulses or other forms of light communication, expanding the ways signals might be found. To handle the huge amounts of data collected, advanced algorithms are used. However, the search has its challenges. The universe is so vast that it's like trying to find a needle in a haystack. Some critics argue that assuming extraterrestrials would use similar communication methods as humans is too narrow of a view. Still, despite these challenges, SETI continues to inspire and represent humanity's curiosity and hope to connect with the unknown. The search for life beyond Earth is a journey filled with wonder and mystery, and the Drake equation is one of the most powerful tools in guiding our exploration. Proposed by Frank Drake in 1961, this equation tries to estimate the number of civilizations in our galaxy capable of communication. While it's based on many unknowns, it helps us understand the factors involved in the search for alien life. The equation includes variables like the rate of star formation, the fraction of stars with planets, the number of habitable planets, and the lifespan of civilizations. Each of these factors holds a piece of the puzzle, but the uncertainty in the values leads to a range of possibilities, from none to millions of potential civilizations. This equation isn't just a formula. It's a way to think about our place in the universe and the chance that we might not be alone. One of the most famous moments in this search happened in 1977, when a strange signal was detected by the Big Ear radio telescope at Ohio State University. The signal, which lasted for 72 seconds, was so unusual that it was dubbed the WOW signal. It appeared on a frequency that's ideal for interstellar communication, and its structure suggested it wasn't a natural phenomenon. Some believe it could have come from an alien civilization, while others think it might have been caused by interference from Earth or an unknown astronomical event. Despite numerous efforts to detect the signal again, it never repeated, leaving its origin a tantalizing mystery that still lingers in the minds of many. The search for extraterrestrial life took a major leap forward with the discovery of exoplanets, planets outside our solar system. With missions like Kepler and TESS, scientists have found thousands of these distant worlds, many of which lie in the so-called habitable zone, where conditions might be just right for life to exist. Some of these exoplanets, called super-Earths, are larger than our planet, but could still have the right conditions for life. Others, like hot Jupiters, are gas giants close to their stars, offering new insights into how planetary systems evolve. As technology improves, with tools like the James Webb Space Telescope, we are learning more about the atmospheres of these planets, searching for signs of life. The discovery of so many diverse worlds makes it seem more likely that we are not alone in the universe, and it fuels our hope of finding life elsewhere. The possibility of discovering intelligent extraterrestrial life raises profound philosophical and societal questions. If we were to make contact, how would it change our view of ourselves and our place in the cosmos? Would we still see ourselves as unique? Or would we understand that we are just one of many civilizations in a vast universe? There are also ethical dilemmas to consider. Should we be actively sending messages to alien civilizations? Or would it be safer to remain silent? And if we do find alien life, especially if it's less advanced, what responsibility do we have toward them? These questions could shape the future of humanity in ways we can't yet imagine. Contact with alien life could bring humanity together in a moment of shared discovery, or it could cause fear and division, depending on the circumstances. DNA is the very essence of life, a molecule that holds the instructions for every living organism, from the smallest bacteria to the most complex humans. It's a molecular code that dictates how organisms grow, function, and reproduce. Discovered in the mid-20th century, DNA's double helix structure opened a new chapter in biology, forever changing our understanding of genetics and life itself. Its discovery, along with the groundbreaking work of scientists like Watson, Crick, Franklin, and others, has revealed the hidden language of life, a language that encodes the vast diversity of organisms on Earth. The story of DNA is not just one of scientific discovery, but of wonder and awe, as it uncovers the deep connections between all living things. The journey to understand DNA started long before its structure was discovered. In the 1860s, a scientist named Friedrich Miescher stumbled upon what he called nuclein, unknowingly identifying DNA. Over time, scientists began to realize that this molecule was responsible for carrying genetic information. In 1953, James Watson and Francis Crick famously described the double helix structure of DNA, a breakthrough that explained how genetic information could be replicated and passed on. The contributions of Rosalind Franklin, who captured the iconic image of DNA using X-ray crystallography, were pivotal in uncovering its shape, though her work was initially overshadowed. The discovery of DNA's structure was a momentous event in science, unlocking the mysteries of heredity and laying the foundation for modern genetics. DNA is often called the language of life because it holds the instructions for building and maintaining every living organism. The structure of DNA consists of 4 bases: adenine, thymine, cytosine, and guanine, that pair together in specific ways to form the steps of a ladder. This sequence of bases is what encodes genetic information, much like how letters form words in a sentence. The process of how this information is used is called transcription and translation. DNA is first transcribed into RNA, which then helps build proteins, the building blocks of life. The genetic code is nearly universal, meaning all living organisms share this language, pointing to a common origin and highlighting the deep connections between life forms on Earth. But DNA is not the only factor that shapes life. Epigenetics is the study of how external factors like diet, stress, and environment can influence how genes are expressed, without changing the underlying DNA sequence. This area of study has revealed how our experiences, and even the experiences of those before us, can affect gene expression. For example, trauma or stress can leave marks on our DNA that may be passed down to future generations, influencing their health. This discovery has opened new doors for understanding diseases like cancer, diabetes, and mental health disorders, offering hope for better treatments in the future. One of the most ambitious scientific projects in history, the Human Genome Project, aimed to map the entire human genome, 3 billion base pairs of DNA, by 2003. This international effort revealed that humans have about 20,000 to 25,000 genes, fewer than initially expected. While only a small fraction of our DNA encodes proteins, the rest plays a crucial role in regulating gene expression and other essential functions. The Human Genome Project also revolutionized technology, making genetic research faster and more affordable. This breakthrough has paved the way for personalized medicine, where treatments can be tailored to an individual's genetic makeup, improving outcomes and reducing side effects. DNA's impact reaches far beyond the laboratory. It has profound implications for society, especially in fields like genetic engineering and ethics. The discovery of tools like CRISPR has made it possible to edit DNA with incredible precision, offering the potential to cure genetic diseases and even improve crops. However, these advances raise ethical questions. Should we be allowed to design our children? What are the implications for privacy as our genetic information becomes more accessible? DNA has also transformed criminal justice, with forensic scientists using it to identify suspects and exonerate the innocent. DNA is not limited to humans. It is the universal molecule of life. Through comparative genomics, scientists study the DNA of different species, revealing the deep evolutionary connections between all life forms. For instance, humans share about 98% of their DNA with chimpanzees, a testament to our close relationship. DNA is also being used to monitor biodiversity through environmental DNA, which helps track species in water, soil, and air. Synthetic biology is another exciting frontier, where scientists design new biological systems, sometimes creating entirely synthetic genomes for use in industry. As we dive deeper into the world of epigenetics, genetic engineering, and the ethical challenges they bring, it's clear that our journey to understand DNA is far from over. The complexity and beauty of DNA remind us of the power of human curiosity and the incredible potential that lies within every living organism. The human brain is an extraordinary marvel, a complex web of neurons that governs our thoughts, emotions, memories, and actions. It is the very core of what makes us who we are, our intelligence, creativity, and the essence of our identity. Yet despite centuries of research and discovery, the brain remains shrouded in mystery. How does it recall past experiences? How does it adapt and heal after injury? And why do conditions like Alzheimer's persist as some of the most puzzling medical challenges? These questions continue to drive our quest for understanding as we delve into the mysteries of the mind, learning more about its capabilities and limitations with each discovery. Memory is at the heart of who we are, allowing us to hold on to past experiences, knowledge, and skills that shape our identity. The way our brain forms and retrieves memories is a fascinating journey of intricate processes. Different regions of the brain work together to create and store memories. The hippocampus helps form new memories and links them to emotions, while the amygdala associates memories with feelings, and the prefrontal cortex helps us make decisions and hold on to information. Memories are categorized into sensory, short-term, and long-term types, each playing a crucial role in how we experience the world. As we encounter new information, the brain encodes it, stores it, and retrieves it when necessary, constantly reshaping itself to strengthen the connections that allow us to remember. This adaptability, known as brain plasticity, ensures that we can learn, grow, and recover from challenges. Brain plasticity, or neuroplasticity, is the brain's remarkable ability to change and reorganize itself throughout life. This ability is especially evident in children, but even as we grow older, our brain can adapt, recover, and learn new things. Structural plasticity involves physical changes in the brain, like growing new neurons or forming new neural connections, while functional plasticity refers to the brain's ability to shift functions from damaged areas to healthy ones. Whether learning a new skill or recovering from an injury like a stroke, the brain shows a remarkable ability to rewire itself. Even in older age, the brain's plasticity can be nurtured through cognitive exercises, physical activity, and social interaction, reminding us that it's never too late to learn or grow. However, not all mysteries of the brain are solved. Some conditions, like Alzheimer's disease, continue to baffle scientists. This progressive disorder steals memories and cognitive function, leaving millions of people and their families in its wake. Alzheimer's is marked by the buildup of harmful plaques and tangles in the brain, which destroy neurons and disrupt communication. Despite significant research, no cure has been found, though promising therapies and early detection methods are being explored. On the other hand, savant syndrome presents a completely different enigma. People with this condition, often with developmental challenges like autism, can demonstrate extraordinary abilities in specific areas like mathematics, art, or music. It's as if the brain, in all its complexity, creates pockets of genius in unexpected places. Some believe that savant abilities arise from the brain's ability to hyperspecialize in unused neural areas, while others suggest it's due to heightened plasticity. The cases of individuals like Kim Peek, whose vast memory made him the inspiration for the movie Rain Man, continue to challenge our understanding of the brain's potential. The story of Phineas Gage, a railroad foreman from the 1800s, provides one of the most striking examples of how the brain's structure influences behavior. After a tragic accident in which a metal rod pierced his skull, Gage miraculously survived. However, his once pleasant and responsible personality changed drastically, making him impulsive and unreliable. This incident helped scientists recognize the crucial role the frontal lobes play in regulating personality and decision-making. Through Gage's story, we began to understand that our brain's physical structure is intricately connected to who we are as individuals. Looking to the future, the field of neuroscience holds incredible promise. With advances in brain imaging technologies, we can peer inside the brain and see its functions in real time. Artificial intelligence is also playing a significant role, helping researchers sift through enormous amounts of data to uncover patterns we might otherwise miss. Gene editing tools like CRISPR offer hope for treating genetic disorders that affect the brain, such as Huntington's disease. But as we continue to unlock the secrets of the brain, we must also navigate ethical questions about privacy and cognitive enhancement. The human brain is a wondrous, mysterious organ. It is an ever-evolving field of study that holds both answers and questions. While we have made tremendous strides, there is still so much more to discover. Conditions like Alzheimer's remind us of the fragility of the mind, while extraordinary phenomena like savant syndrome remind us of the brain's remarkable potential. With each new discovery, we take another step closer to understanding the vast and intricate network that defines us as human beings. The universe is a vast and mysterious expanse, stretching far beyond what we can see with our eyes. While the stars, planets, and galaxies we observe from a beautiful cosmic picture, they only make up a small portion of everything that exists. The rest of the universe is hidden in the form of two perplexing components: dark matter and dark energy. Together, they account for about 95% of the cosmos, yet their true nature remains one of the greatest unsolved mysteries in science, leaving us with endless questions.
What are they?
How do they shape the universe? These are the questions that continue to inspire awe and wonder as we look to the stars. Our understanding of the universe has come a long way. In ancient times, people saw the heavens as a dome filled with stars and gods, a place of mystery but also familiarity. Today, we know much more thanks to centuries of scientific discoveries. According to modern cosmology, the universe is made up of ordinary matter, and dark energy. Ordinary matter, the stuff we can see and touch, makes up just 5% of the universe. Dark matter, an invisible substance that doesn't emit light but still exerts gravity, accounts for 27%. The remaining 68% is dark energy, a mysterious force that drives the universe's accelerated expansion. Though we can't see or touch dark matter and dark energy, their effects are felt throughout the cosmos, guiding the motion of galaxies and shaping the very structure of the universe. The search for dark matter began with an unexpected discovery in the 1930s by Swiss astronomer Fritz Zwicky. While studying galaxies in the Coma cluster, he realized the galaxies were moving too quickly for the visible matter in the cluster to provide enough gravitational pull to hold them together. He proposed that an unseen form of matter, which he called dark matter, must be responsible for this extra gravity. In the 1970s, astronomer Vera Rubin provided further evidence when she studied the rotation of galaxies. She found that stars at the edges of galaxies were moving just as fast as those near the center, contradicting what we would expect from Newtonian physics. This suggested the presence of invisible mass. The search for dark matter intensified with the observation of gravitational lensing, where light from distant galaxies bends around unseen objects, revealing more mass than can be seen. As we dive deeper into the enigma of dark matter, scientists have developed theories about what it might be. One possibility is that dark matter is made up of particles called WIMPs that are weakly interacting massive particles, which interact only through gravity and weak nuclear forces. Other theories suggest dark matter could be composed of axions, light particles that might explain some of its behaviors, or sterile neutrinos, a type of neutrino that interacts very weakly with matter. To detect these particles, scientists use different approaches, such as direct detection, where they look for interactions between dark matter particles and ordinary matter, and indirect detection, where they study the byproducts of dark matter decay or annihilation. High-energy experiments like those at the Large Hadron Collider also aim to create conditions where dark matter particles might appear. The LHC, the world's largest particle accelerator, has been a key tool in the search for dark matter. Scientists hope that by smashing protons together at near-light speeds, they can recreate the conditions of the early universe and observe dark matter particles in action. Although the LHC has made groundbreaking discoveries, such as the detection of the Higgs boson, it has not yet found direct evidence of dark matter. Despite these challenges, scientists remain hopeful that future experiments and upgrades to the LHC will provide the breakthroughs needed. Another promising avenue of research is direct detection experiments, such as the Large Underground Xenon experiment in South Dakota. Here, a tank filled with liquid xenon, shielded from cosmic rays deep underground, is used to search for dark matter particles. When a dark matter particle interacts with a xenon atom, it produces a faint flash of light that scientists can measure. Other experiments, like Xenon 1T in Italy and the Dampy satellite, are also attempting to detect dark matter. But so far, the elusive particles have not been found. The search continues as each experiment brings us one step closer to understanding the unknown. In addition to dark matter, there is the mystery of dark energy, which plays a different yet equally important role in the universe. In the late 1990s, two teams of astronomers discovered that the universe's expansion is not slowing down as previously expected, but accelerating. This surprising finding was attributed to dark energy, a force that counteracts gravity and pushes galaxies farther apart. Dark energy is thought to be related to the energy of empty space, which was first proposed by Albert Einstein as the cosmological constant. The influence of dark energy means that the universe will continue to expand indefinitely, possibly leading to a big freeze where galaxies drift apart and stars eventually burn out. As scientists work to unravel the mysteries of dark matter and dark energy, new theories and experiments are continually being developed. Some scientists suggest that dark matter and dark energy may be connected, manifestations of the same underlying phenomenon. Future observatories like the James Webb Space Telescope and the Vera C. Rubin Observatory are expected to provide new insights into the dark universe. In addition, the growing role of artificial intelligence in analyzing vast amounts of data will help identify patterns and accelerate discoveries that might otherwise go unnoticed. The search for dark matter and dark energy is more than just a scientific endeavor. It is a testament to humanity's curiosity and determination to understand the cosmos. These unseen forces shape the universe in ways we are just beginning to understand. As technology advances and new discoveries are made, we continue our journey into the dark universe, hopeful that the mysteries of dark matter and dark energy will one day be revealed. Throughout the course of human history, great civilizations have risen to remarkable heights, only to disappear into the shadows of time, leaving behind only faint traces of their once thriving existence. These lost civilizations stir our imaginations, filling us with wonder and curiosity about their remarkable achievements, mysterious decline, and ultimate vanishing. The reasons for their fall remain uncertain. Was it the result of natural disasters, environmental changes, internal conflict, or something more elusive? These questions fuel a sense of mystery as we try to understand the causes of their collapse and imagine the lives of those who once flourished. One of those stories is that of Atlantis, the fabled island kingdom mentioned by the Greek philosopher Plato. Plato described Atlantis as a powerful and advanced society that suddenly sank beneath the ocean in a cataclysmic event. According to Plato, the Atlanteans were a prosperous people with advanced technology, agriculture, and military might. Yet their arrogance and corruption angered the gods, leading to their downfall. Scholars have speculated about Atlantis's possible location, from the Mediterranean to Antarctica, or even South America. Some believe the story may be based on real events, like the volcanic eruption of Thera, which devastated the Minoan civilization. Others suggest that Atlantis was a symbolic tale meant to warn of the dangers of greed and moral decay. In Central America, the Maya civilization also rose to great heights before its mysterious decline. The Maya were known for their stunning architecture, advanced mathematical knowledge, and precise astronomy. Cities like Tikal and Chichen Itza boasted towering pyramids and expansive ceremonial plazas. Their complex calendars tracked celestial movements, and their written language preserved their history and myths. Yet, despite these remarkable achievements, the Maya civilization began to decline long before the arrival of the Spanish in the 16th century. Many theories exist regarding the collapse, with some pointing to environmental factors like deforestation and drought, while others highlight internal conflict and warfare between city-states. Ultimately, the Maya civilization was further weakened by the devastation brought by European colonization. In another part of the world, the Indus Valley civilization flourished between 3300 and 1300 BCE in what is now Pakistan and northwest India. This early urban culture was known for its sophisticated city planning, with cities like Mohenjo-Daro and Harappa featuring grid layouts and advanced drainage systems. The Indus Valley had an extensive trade network, exchanging goods with Mesopotamia. However, much about their society remains a mystery, as their written language remains undeciphered. The reasons behind the decline of the Indus Valley civilization are still debated, with climate change, shifts in the flow of rivers, and possible invasions all being proposed as possible causes. Another site that challenges our understanding of ancient civilizations is Göbekli Tepe in Turkey. Dating back to 9600 BCE, this archaeological site is older than many of the earliest known farming communities. Unlike other monumental structures, Göbekli Tepe was built by hunter-gatherers, suggesting that social organization and religious expression may have existed long before the advent of agriculture. The site is made up of massive stone pillars adorned with intricate carvings of animals and symbols. Its purpose remains uncertain, but it is believed to have served as a ceremonial or spiritual center, shedding light on the significance of religion and ritual in early human societies. Göbekli Tepe challenges the traditional narrative of human history, showing that complex social structures and shared beliefs were present long before settled farming communities. Each of these civilizations, with their remarkable achievements and mysterious disappearances, leaves behind more questions than answers. As we uncover more about their cultures, their rise and fall, we are reminded of the fragility of human existence and the enduring fascination with the lost worlds of the past. The disappearance of lost civilizations is a mystery that continues to captivate our imagination, leaving us to wonder what happened to these once great societies. Each civilization's decline is unique, but as we dig deeper, we begin to see common threads that offer some clues. Environmental factors often played a significant role. Changes in climate, such as prolonged droughts or flooding, could devastate societies that relied on agriculture to survive. Natural disasters like earthquakes, volcanic eruptions, and tsunamis could strike without warning, wiping out entire civilizations in a matter of days, as seen with the Minoans after the eruption of Thera. Alongside nature's forces, human conflict also played its part. Wars, invasions, and internal struggles weakened societies, such as when the mighty Aztec Empire fell to Spanish conquistadors. Even economic decline, when resources were overused or trade routes were disrupted, could slowly chip away at a civilization's strength, making it vulnerable to collapse. Sometimes we are left with no answers at all. Some civilizations disappeared without any clear explanation, sparking wild theories about pandemics, extraterrestrial influences, or even hidden vulnerabilities that we still don't understand. As we reflect on the rise and fall of these ancient civilizations, there are powerful lessons to be learned. One of the most important is resilience, the ability to adapt and innovate in the face of overwhelming challenges. The Inca, for example, created terraces on steep mountainsides to grow crops, while the Maya built sophisticated water reservoirs to manage scarce water resources. These societies showed us how human ingenuity could overcome even the harshest of environments. But there is also a cautionary tale to be found in the collapse of civilizations like Easter Island. There, the overuse of natural resources led to deforestation and environmental collapse, reminding us of the importance of living in balance with nature. Even in their decline, lost civilizations left behind treasures of knowledge, art, and architecture that continue to inspire us today. The remnants of their achievements remind us that even in our weakest moments, we have the potential to create something enduring. The story of lost civilizations is a reminder of the fragility of human achievement, and yet it also speaks to the power of human curiosity. From the legendary Atlantis to the ancient site of Göbekli Tepe, these civilizations offer us a window into the past that helps us understand not just where we've come from, but how we might shape a better future. As we continue to uncover the secrets of these ancient societies, we are reminded that the lessons they left behind are not just about history. They are about the choices we make today and how we can create a more sustainable, resilient world for generations to come. The ocean, vast and mysterious, covers more than 70% of the Earth's surface, yet its depths remain one of the most unexplored and enigmatic areas of our planet. Beneath the surface lies a world of extremes: crushing pressure, perpetual darkness, and incredible biodiversity. For centuries, humans have gazed upon the ocean with a sense of wonder, captivated by its vastness and hidden secrets. Yet, only in recent decades, with the aid of advanced technology, have we started to scratch the surface of what lies beneath. From the Mariana Trench's haunting depths to the curious ecosystems surrounding hydrothermal vents, the ocean holds clues to Earth's history, evolution, and perhaps even the origins of life itself. It's a realm where the unknown beckons us, urging exploration and discovery. We will first dive into the sheer scale and complexity of the ocean, which is divided into distinct zones, each with unique characteristics and challenges for exploration. The epipelagic zone, where sunlight filters through the waters, is home to the creatures that thrive in the light. Beneath it lies the mesopelagic zone, or the twilight zone, where creatures like lanternfish have adapted to the dim light. Deeper still, the bathypelagic zone, known as the midnight zone, is a place of total darkness, and the abyssopelagic zone follows, where near-freezing temperatures and immense pressure make survival nearly impossible. The hadopelagic zone, the deepest part of the ocean, resides in oceanic trenches such as the Mariana Trench, which holds Earth's greatest mysteries. These deep regions are challenging to explore due to the crushing pressure, freezing temperatures, and darkness. But technology has allowed us to venture deeper than ever before. The first successful descent to the Challenger Deep in 1960 by Jacques Piccard and Don Walsh marked a monumental achievement. In 2012, filmmaker James Cameron made his own solo journey to the depths, capturing haunting footage of the barren alien landscape. The ocean trenches, like the Tonga Trench and the Puerto Rico Trench, hold potential for groundbreaking discoveries, from unique geological formations to the microbial life that thrives in extreme conditions. The bizarre world of deep-sea creatures, many of which remain undiscovered. These creatures have evolved extraordinary adaptations to survive in the harsh conditions of darkness, cold, and high pressure. Bioluminescent species, such as deep-sea squid and lanternfish, use light to communicate, camouflage, and hunt. The giant squid, once thought to be a myth, was only confirmed to exist in the 19th century, and in 2004, researchers captured the first live footage of this elusive creature. Extreme survivors like the barrel-eye fish with its transparent head and the yeti crab found near hydrothermal vents continue to astound scientists. Hydrothermal vent ecosystems discovered in the late 1970s along mid-ocean ridges. These vents, spewing superheated water rich in minerals, support life in the complete absence of sunlight. The organisms that thrive here, like tube worms and vent crabs, use chemosynthesis to create energy, offering a glimpse into how life might have originated on Earth. These ecosystems also provide insight into extremophiles, organisms that could survive on other planets. These findings have expanded our understanding of the deep sea, and microbial discoveries near hydrothermal vents hold potential for revolutionary advances in medicine and energy. Despite our progress, only a fraction of the ocean floor has been mapped in detail. With the help of technological innovations like autonomous underwater vehicles, deep-sea rovers, and submersibles, scientists are continuing to push the boundaries of exploration. Collaborative efforts by organizations like the Schmidt Ocean Institute and NOAA's Office of Ocean Exploration promise to uncover even more secrets hidden beneath the waves, from new species to potential resources that could benefit humanity. In conclusion, the ocean depths remain one of the greatest mysteries of Earth. From the crushing pressure of the Mariana Trench to the thriving ecosystems of hydrothermal vents, these unexplored regions hold the potential to change our understanding of life and the world itself. As technology continues to evolve, humanity stands on the edge of incredible discoveries. The quest to explore the ocean is not just about uncovering the unknown, but also a reflection of our unrelenting curiosity and our desire to understand the world around us. Death is something that touches everyone, regardless of where they come from or what they believe. It is inevitable, a part of life that shapes our every moment. Yet it is also one of the greatest mysteries, making us wonder, what happens when we die? Is death just an end, or is it a new beginning? We all feel the weight of life's fragility and wish for some kind of permanence, even though we know that nothing lasts forever. This quest for understanding has led humans to ask these big questions for centuries, with philosophers, scientists, and religious thinkers offering a wide range of answers. This essay will take a close look at death, exploring how different cultures view the afterlife, the mysterious experiences that some people have when they come close to death, and the deep thoughts about mortality that have shaped human thought throughout history. By doing this, we aim to gain a better understanding of our shared experience with death, something that connects all of humanity. Death is not viewed the same way everywhere. Different cultures and belief systems offer unique views on what happens after we die. These beliefs shape the way people live and die. In the West, religions like Christianity, Judaism, and Islam provide different answers. For Christians, death is seen as a doorway to eternal life, with the soul either going to heaven, hell, or purgatory. Judaism has varying views, but the concept of the world to come and resurrection is common. In Islam, death marks a transition to the eternal, with the soul's fate determined by one's actions during life. Meanwhile, Eastern religions like Hinduism, Buddhism, and Taoism offer their own perspectives. Hindus believe in samsara, the cycle of life, death, and rebirth, where the goal is to break free and reach liberation. Buddhism, with its similar views, focuses on achieving enlightenment or nirvana to end the cycle of suffering. Taoism, on the other hand, sees death as a natural part of the universe's flow, encouraging acceptance. Indigenous cultures also offer different insights. Many African cultures view death as a continuation in the spirit world, where ancestors guide the living. Native American beliefs emphasize the journey to a spiritual realm, while shamanistic traditions often view death as a transformation into something greater. Another intriguing aspect of death is the phenomenon of near-death experiences, NDEs, where people report vivid and often life-changing experiences when they come close to dying. Common themes in NDEs include traveling through a tunnel towards a bright light, feeling intense peace and love, and meeting deceased loved ones. Some even describe a life review, where they relive key moments of their lives with deep emotional understanding. Though these experiences are powerful and transformative, scientists have debated their causes. Some suggest that these visions are linked to brain activity, such as a lack of oxygen or chemical changes in the brain, while others believe they might point to something beyond the physical world. Despite these differing explanations, NDEs remain a deeply personal and often spiritual experience for many. Philosophy has long wrestled with the idea of death, offering different perspectives on its meaning. Existentialist thinkers like Jean-Paul Sartre and Martin Heidegger argued that confronting death is key to understanding life. Rituals surrounding death offer comfort and meaning. They vary greatly across cultures, but often serve as ways to honor the deceased and help the living cope. Funerals and ceremonies such as burial or cremation symbolize respect for the body and the journey to the afterlife. Some traditions, like Tibetan sky burials or Egyptian mummification, reflect different beliefs about what happens after death. Mourning customs also vary, with Western cultures often focusing on wearing black and holding memorial services, while in Japan, Buddhist rituals are performed for the deceased. In Mexico, Dia de los Muertos is a vibrant celebration of life and death, where families honor their ancestors with offerings and festivities. Science and technology continue to reshape our understanding of death. Today, death is often defined by the irreversible cessation of brain activity. Ethical dilemmas arise around cases where life support is used or when people are in persistent vegetative states. Technologies like cryonics, which preserves bodies in the hope of future revival, challenge our ideas about death and identity. As the digital age grows, new concepts like digital immortality, preserving a person's online presence after death, are emerging, raising questions about the nature of legacy and identity. Reflecting on death can teach us many valuable lessons about life. Cultures across the world have found ways to view death not as an end, but as a transformation, a passage that connects the living and the dead. Rituals, practices, and beliefs help us understand and accept our mortality, providing comfort and strength. On a personal level, awareness of death can inspire gratitude, focus, and compassion, teaching us to live more fully and love more deeply. In the end, understanding death allows us to better appreciate life, giving us the chance to leave a meaningful legacy that transcends time. Human existence has always been a mystery, a deep question that stirs curiosity and wonder in all of us. Why are we here? What is the purpose of our lives? Is there one universal meaning, or do we each create our own? These questions challenge us every day and shape the way we live, love, and dream. Over the centuries, thinkers from every field, philosophers, scientists, theologians, and artists, have sought to answer these profound questions in different ways. Some find purpose in belief, others in science, and still others in personal experiences. This exploration of the meaning of life is something that binds us together as human beings, no matter where we come from or what we believe. Philosophy has long been the cornerstone of humanity's search for purpose. Throughout history, different thinkers have offered unique answers to the question of why we exist. One prominent school of thought is existentialism, which argues that life itself has no inherent meaning. Instead, it is up to each person to create their own purpose through choices and actions. Thinkers like Soren Kierkegaard, Jean-Paul Sartre, and Albert Camus have explored this idea. Kierkegaard emphasized that finding meaning is a personal journey, often tied to faith, while Sartre famously stated that existence precedes essence, meaning we must define ourselves through our actions. Camus, in his work The Myth of Sisyphus, explored the absurdity of life, suggesting that the lack of meaning could actually bring freedom and personal happiness. In contrast, theistic traditions such as Christianity, Islam, and Hinduism see life's purpose as coming from a divine creator. In these beliefs, humans are meant to worship, grow morally, and strive for spiritual enlightenment. On the other hand, nihilism, popularized by Friedrich Nietzsche, suggests that life is inherently meaningless, and any search for purpose is futile. However, Nietzsche also believed that embracing this lack of meaning could empower individuals to create their own values and live authentically. While philosophy tackles the abstract ideas of purpose, science looks for more concrete answers about why humans exist. Evolutionary biology, for instance, suggests that our existence is a result of natural selection, with survival and reproduction being our primary purposes. Charles Darwin's theory of evolution explained how traits that improve survival are passed down through generations. But beyond survival, human evolution also highlights the importance of cooperation and altruism in building societies. In the realm of cosmology, the study of the universe's origins and structure offers another perspective on human existence. The Big Bang Theory suggests that the universe began billions of years ago, and our existence is just a small moment in the vast timeline of the cosmos. Some scientists propose the anthropic principle, which argues that the universe seems fine-tuned for life, leaving open the possibility of a greater purpose behind our existence. Viktor Frankl, a psychiatrist and Holocaust survivor, brought a deeply personal and psychological perspective to the search for meaning. In his book, Man's Search for Meaning, Frankl introduced the concept of logotherapy, a therapeutic approach focused on finding meaning even in the face of suffering. He observed that those who found purpose, whether through love, faith, or hope, were more likely to endure unimaginable hardship. Frankl identified three main sources of meaning: work or achievement, relationships and love, and how we face suffering. His ideas remind us that purpose is not something given to us externally, but something we discover within ourselves, regardless of our circumstances. Across the world, cultures offer their own interpretations of human purpose. Western cultures often emphasize individual fulfillment and personal achievement, while many Eastern cultures focus on community harmony and duty. Myths and stories from different traditions also offer valuable lessons on purpose. Greek mythology, for instance, teaches about the hero's journey and the consequences of pride, while indigenous cultures often view humanity's purpose as caretakers of the earth, emphasizing our connection to nature. In today's fast-paced, interconnected world, finding purpose can feel more challenging than ever. The digital age, while offering opportunities for connection, also fosters feelings of disconnection and meaninglessness. Social media can amplify existential doubt as people compare their lives to others. Yet, research shows that having a sense of purpose is linked to better mental health, resilience, and even longevity. Programs like mindfulness and therapy emphasize the importance of finding meaning in life to improve well-being. Reflecting on humanity's different approaches to finding meaning teaches us that there is no single answer. Each person's journey is unique, and the search for purpose is a deeply personal one. At the same time, embracing diverse perspectives enriches our understanding and helps us see the beauty in all the different ways people find meaning. Whether in everyday moments, relationships, or personal growth, purpose is not always about grand achievements, but about how we live our lives and what we make of the time we have. In the end, the search for meaning is as much about the journey as it is about the destination, a journey that unites us all in our shared humanity. Dreams have intrigued and fascinated humanity for centuries. They stir our curiosity, sparking questions about their purpose and meaning. Why do we dream? Are dreams just random byproducts of sleep, or do they serve a deeper function in our lives? From ancient cultures that viewed dreams as divine messages to modern science that examines the biological mechanisms behind them, dreams have been interpreted in countless ways. Dreams occur during a special phase of sleep called REM, rapid eye movement sleep. This phase is crucial for understanding the biological processes behind dreaming. Sleep itself is divided into two main stages: non-REM sleep, which includes light and deep sleep, and REM sleep, where vivid dreams occur. As we enter REM sleep, our brain becomes highly active, resembling wakefulness, and our muscles temporarily paralyzed to prevent us from physically acting out our dreams. The eyes move rapidly beneath closed lids, though the purpose of these movements is still not fully understood. REM sleep plays a significant role in emotional regulation, memory processing, and overall cognitive function. Without adequate REM sleep, we can experience mood swings, difficulty learning, and heightened stress, which shows just how important it is for our mental health. Over time, many theories have tried to explain why we dream, each offering a unique perspective. Sigmund Freud, the father of psychoanalysis, believed dreams were a window to the unconscious mind. In his famous work, The Interpretation of Dreams, Freud argued that dreams reveal repressed desires and unresolved conflicts. According to him, dreams are a form of wish fulfillment, allowing us to express desires we might be too afraid to acknowledge in our waking life. Carl Jung, a student of Freud, took a different approach, suggesting that dreams help us integrate both our conscious and unconscious selves. He introduced the idea of the collective unconscious, a shared set of symbols or archetypes that appear in dreams across different cultures. Modern neuroscience, on the other hand, suggests that dreams are a byproduct of the brain trying to make sense of random neural activity during REM sleep. Some scientists believe dreams help consolidate memories, process emotions, and even rehearse situations we might encounter in life. Throughout history, dreams have also held profound cultural significance. Many ancient societies viewed dreams as divine messages or glimpses into the future. In ancient Egypt, dreams were seen as communications from gods, with temples dedicated to helping people seek guidance through dreams. The ancient Greeks and Romans also placed great importance on dreams, consulting oracles and interpreters to gain insights into battles or life decisions. In indigenous cultures, such as Native American and Aboriginal Australian traditions, dreams were viewed as spiritual experiences connecting people to their ancestors and the natural world. Even in religious texts like the Bible and the Quran, dreams played an important role, with figures like Joseph and Daniel interpreting dreams as divine revelations. These cultural perspectives remind us that dreams have always been more than just an internal experience. They have been seen as a bridge to the unseen world. Beyond their cultural and spiritual meanings, dreams also have a psychological and emotional impact on us. For some, dreams can be a source of deep anxiety, especially when nightmares arise from stress, trauma, or unresolved fears. Nightmares may serve as a way for our minds to process these emotions and prepare for threats. On a different note, lucid dreaming, where the dreamer becomes aware of and can control their dreams, has been used therapeutically to confront fears and unlock creative potential. Recurring dreams, which often involve common themes like falling or being chased, can offer valuable insights into unresolved issues or anxieties in our waking lives. These types of dreams encourage self-reflection and can help us confront the challenges we face. As science continues to advance, new methods of studying dreams are emerging. Researchers are exploring ways to decode dream content using brain imaging techniques, though this field is still in its early stages. In therapy, dream research is already being used to treat conditions like PTSD, with techniques that modify nightmares to help people process trauma. However, these advancements also raise ethical questions, such as whether dream data should remain private or if it could be used for commercial purposes. As our understanding of dreams continues to grow, we will likely gain new insights into how they shape our lives and influence our minds. In conclusion, dreams are a fascinating intersection of biology, psychology, and culture, revealing the complexity of the human experience. Whether seen as messages from the divine, the result of brain activity, or a way to process emotions, dreams are an essential part of our lives. As we continue to explore this timeless mystery, we may uncover even deeper layers of understanding about the role dreams play in shaping who we are and how we navigate the world. The world is filled with incredible monuments that seem to defy time and space, standing as a testament to the brilliance and ambition of ancient civilizations. Among these are the Great Pyramids of Giza, the mystical Stonehenge, and the awe-inspiring city of Machu Picchu. These structures, built long before modern machinery, raise fascinating questions. How did these ancient people construct such massive buildings? What drove them to take on such monumental tasks? Building these colossal structures was no small feat, even with today's advanced technology. Ancient civilizations faced challenges that seem impossible by today's standards. The massive stones used in these constructions were often several tons in weight, like the 80-ton limestone blocks in the Great Pyramids or the 25-ton sarsen stones at Stonehenge. Moving these giant stones required inventive techniques and well-coordinated labor. Additionally, many of these structures were aligned with the stars and the sun, demanding incredible precision and astronomical knowledge. The building of these monuments was not just about physical labor, but about coordinating vast teams of workers, ensuring food, shelter, and safety. These projects required advanced organizational skills and a deep understanding of natural forces and materials, showcasing the extraordinary abilities of ancient people. The methods used to construct these megalithic structures have long been debated. For instance, it was once believed that slaves built the pyramids, but recent discoveries suggest that many of the workers were skilled laborers who were well-fed and housed in workers' villages. These workers were organized into teams with specialized roles: stonecutters, transporters, and builders. Techniques like copper chisels, dolerite hammers, and wooden ramps were used to cut and transport the stones. The workers also used basic principles of leverage and ramps to lift heavy stones into place, while some researchers proposed that wetting the sand in front of sledges helped reduce friction during transportation. The innovation behind these methods, although simple by modern standards, reveals how much ancient societies understood about physics, engineering, and teamwork. One of the most iconic examples of ancient engineering is the Great Pyramids of Giza, which were built over 4,500 years ago. These massive structures, especially the Great Pyramid, are made up of millions of limestone blocks, with an estimated total weight of 6 million tons. The construction of the pyramids required thousands of workers and several decades to complete. The precision with which the Great Pyramid is aligned to the cardinal points, north, south, east, and west, shows that the builders used advanced surveying tools and techniques. These pyramids were not just tombs, they symbolized the pharaoh's divine power and his connection to the gods, making their construction a national effort that united the people. Stonehenge, located in England, is another extraordinary megalithic structure that has sparked curiosity and wonder for centuries. Built around 3000 BCE, Stonehenge was constructed in phases over 1,500 years. Large sarsen stones and smaller bluestones were moved from distant locations, sometimes over 150 miles away. The bluestones were transported by river and sledges, while the larger sarsen stones were dragged with the help of manpower and wooden rollers. Stonehenge's alignment with the sun suggests it was used for astronomical observation and religious ceremonies. Excavations at the site also reveal that it was used as a sacred burial ground, and recent theories suggest that it may have served as a site for communal gatherings, bringing together people from various regions. High in the Andes Mountains of Peru lies Machu Picchu, a breathtaking Incan city that was built in the 15th century. Machu Picchu's construction was a remarkable achievement, given the rugged terrain and its high-altitude location. The Incas built agricultural terraces to prevent erosion and created intricate water systems to manage the flow of water. The massive stones used to build the city were precisely cut and fit without the use of mortar, allowing the structures to survive the frequent earthquakes in the region. Machu Picchu was likely a royal estate or spiritual center, designed with a deep connection to the surrounding mountains and celestial events. Rediscovered in 1911 by Hiram Bingham, it has become a symbol of Incan innovation and resilience. The construction of these megalithic structures teaches us important lessons about human ingenuity and cooperation. Ancient builders used locally sourced materials and designed their structures to blend with their natural surroundings, showing us the value of sustainability. These projects required people to work together, combining their skills and efforts for a common purpose. The sheer scale of these undertakings demonstrates what can be achieved when people unite for a shared goal. These monuments have endured through centuries, inspiring awe and curiosity in all who encounter them, reminding us of the potential humanity has to create something truly lasting and meaningful. The Great Pyramids, Stonehenge, and Machu Picchu stand as awe-inspiring monuments to the creativity and determination of ancient civilizations. By exploring the methods used to build these incredible structures, we not only learn about the tools and techniques of the past, but also connect with the dreams and aspirations of those who built them. These monuments are enduring reminders of what can be achieved through imagination, perseverance, and collaboration, leaving legacies that continue to inspire us today. Antimatter, a concept once confined to the realm of science fiction, is now one of the most fascinating mysteries in modern physics. First predicted in the early 20th century and later confirmed experimentally, antimatter mirrors ordinary matter in many ways, but is fundamentally different. For every particle of matter, there exists an antiparticle with the same mass but opposite charge and properties. When these particles and antiparticles meet, they annihilate each other, releasing an incredible burst of energy. But despite this symmetry, antimatter is mysteriously rare in the universe. Why does matter seem to dominate, while antimatter appears to have vanished? This question remains at the heart of the cosmic puzzle that scientists are determined to solve. To understand antimatter, it's important to first look at its basic definition and properties. Antimatter consists of antiparticles, which are counterparts to the particles that make up ordinary matter. These antiparticles have the same mass as their corresponding particles, but opposite charges. For example, the positron is the antiparticle of the electron, carrying a positive charge instead of a negative one. Similarly, an antiproton has the same mass as a proton, but carries a negative charge. When a particle meets its antiparticle, they destroy each other in a process known as annihilation, converting their mass into pure energy. This interaction releases a tremendous amount of energy, as predicted by Einstein's famous equation E equals mc squared. According to the laws of quantum mechanics, antimatter arises naturally and is predicted to exist in equal amounts to matter, as part of the universe's symmetry. However, there is a mystery. If antimatter and matter should have been created in equal amounts after the Big Bang, why does our universe seem to be made almost entirely of matter? After the universe began, about 13.8 billion years ago, it was an incredibly hot and dense place, where matter and antimatter existed side by side. As the universe cooled, most of the matter and antimatter annihilate each other, leaving behind only a small amount of matter. This imbalance is known as the matter-antimatter asymmetry, and scientists have long been puzzled by its cause. Several theories attempt to explain this, including CP violation, a process where certain particles behave differently from their antiparticles, and baryogenesis, a hypothetical process that could have created more matter than antimatter in the early universe. Yet the exact reason why antimatter didn't dominate remains one of the most profound, unanswered questions in physics. The discovery of antimatter was a breakthrough in particle physics. In 1928, physicist Paul Dirac predicted the existence of particles with the same mass as electrons, but opposite charges. Though initially considered a mathematical oddity, this idea led to the discovery of the positron in 1932 by Carl Anderson. Anderson observed a particle with the same mass as an electron but with a positive charge, confirming Dirac's prediction and providing the first experimental evidence for antimatter. This discovery earned Anderson the Nobel Prize in Physics in 1936. Further experiments led to the creation of antiprotons and antineutrons in the 1950s, which confirmed the existence of antiparticles even further. These discoveries laid the foundation for modern high-energy particle physics and opened the door to studying antimatter in more depth. Today, antimatter is studied in controlled environments, though it is incredibly difficult to produce and store. Particle accelerators, such as those at CERN, routinely create antiparticles by smashing protons together at high speeds. These collisions recreate the extreme conditions that existed just moments after the Big Bang, allowing scientists to study the particles that result. While antimatter is rare in nature, scientists have learned how to create small amounts of it in laboratories, using powerful magnetic traps to contain the antiparticles. These studies have led to important applications such as positron emission tomography or PET scans, which use positrons to help detect conditions like cancer. There are even theoretical proposals for using antimatter as a powerful fuel source for space travel. However, producing and storing antimatter remains a huge challenge, and the energy required to create it far exceeds what can be recovered. At CERN, the world's largest particle accelerator, scientists are working on some of the most cutting-edge experiments to unlock the mysteries of antimatter. The Large Hadron Collider at CERN simulates conditions similar to those just after the Big Bang by smashing protons at nearly the speed of light. These collisions produce a wide range of particles, including antiparticles, and offer scientists a chance to study them in detail. CERN also runs a dedicated antimatter factory, where researchers create and trap particles like antiprotons and antihydrogen. One of the key experiments being conducted is the Alpha experiment, which is studying antihydrogen to understand whether antimatter behaves the same way as matter under the influence of gravity and other forces. Black holes are among the most mysterious and awe-inspiring phenomena in the universe, capturing both our imagination and our deepest fears. They are the ultimate expression of nature's power, formed from the remnants of massive stars that collapse under their own gravity. In these dark regions of space, the rules of physics seem to break down, with gravity so intense that not even light can escape. As we try to understand them, black holes challenge everything we know about space and time, from the event horizon where no escape is possible, to the singularity at their heart, where gravity reaches infinity. Black holes hold secrets that continue to elude us. At their core, black holes are regions of space where gravity is so powerful that it warps the fabric of space-time. This intense gravitational force creates a point of no return, known as the event horizon. Once anything crosses this boundary, whether it's light, matter, or energy, there is no escape. Black holes can form in a few different ways. Stellar black holes are born when a massive star runs out of fuel and collapses under its own weight, turning into a singularity, a point of infinite density. Supermassive black holes, which lie at the centers of galaxies, are millions to billions of times the mass of our Sun. And though their formation is still debated, they likely grew from the merging of smaller black holes or the collapse of giant gas clouds. There are even hypothetical primordial black holes that might have formed right after the Big Bang due to density fluctuations. Despite their terrifying nature, black holes are not just voids of nothingness. They have structure, with an event horizon, a singularity at their core, and an accretion disk made of swirling material that heats up as it spirals inward. The event horizon and singularity are two of the most important and puzzling features of a black hole. The event horizon marks the point where gravity becomes so strong that nothing can escape. Once something crosses this boundary, it is pulled inexorably toward the singularity. The size of this boundary, called the Schwarzschild radius, depends on the mass of the black hole. For instance, a black hole with the mass of the Sun would have an event horizon just 3 kilometers across. The singularity, at the very center of a black hole, is where all matter is crushed into an infinitely dense point, and the laws of physics as we understand them break down completely. Time and space lose their meaning near this point, and the theories of quantum mechanics and general relativity must be reconciled to explain what happens here. Inside a black hole, we can only speculate about what occurs, but some ideas have been proposed. As an object approaches a black hole, the tidal forces stretch it out like spaghetti in a process known as spaghettification. Time also behaves strangely near the event horizon. It slows down relative to an outside observer, and at the event horizon itself, time seems to stop altogether. Once inside the event horizon, there is no turning back, and the object's fate is sealed with all paths leading toward the singularity. For small black holes, the tidal forces would tear anything apart long before reaching the center. However, in supermassive black holes, these forces are weaker near the event horizon, so objects could survive longer before being stretched and compressed. Some scientists even speculate that black holes could serve as gateways or wormholes to other regions of space or alternate universes. Understanding what truly happens inside a black hole may one day require a new theory that unifies quantum mechanics with general relativity. In recent years, the Event Horizon Telescope has provided a stunning breakthrough in black hole research. In 2019, the EHT captured the first ever image of a black hole's shadow located in the galaxy M87, 55 million light-years away. This momentous achievement confirmed the existence of black holes and validated predictions made by Einstein's theory of general relativity. The EHT works by combining the data from a global network of radio telescopes, creating a virtual telescope as large as the Earth itself. This allows scientists to observe the glowing accretion disks around black holes and infer the size and shape of their event horizons. Looking ahead, scientists hope to capture more images, including one of the supermassive black hole at the center of our own galaxy, Sagittarius A*, and refine their techniques to observe these incredible objects with even greater detail. Another exciting concept is Stephen Hawking's theory of Hawking radiation, which suggests that black holes are not completely black, but instead they emit radiation due to quantum effects near the event horizon. This radiation occurs because of virtual particles that constantly form and annihilate in empty space. Near the event horizon, one of these particles can fall into the black hole, while the other escapes, leading to a gradual loss of mass for the black hole. Over incredibly long periods, this process could cause black holes to shrink and eventually evaporate entirely, potentially ending in a burst of high-energy particles. Although Hawking radiation has not been observed directly, it presents a fascinating possibility. Black holes may not be eternal after all. But the theory also raises complex questions, especially about the information contained within a black hole. If a black hole evaporates, where does the information about the matter it contained go? This is a mystery that remains unsolved. Black holes are more than just cosmic oddities. They play vital roles in the evolution of galaxies and the universe as a whole. Supermassive black holes, for instance, may regulate star formation in galaxies by interacting with the surrounding gas and energy. There is also a relationship between the mass of a galaxy's central black hole and its structure. By studying black holes, scientists are testing the limits of our understanding of physics, exploring how general relativity and quantum mechanics come together in these extreme environments. In a way, black holes serve as laboratories for studying the universe in its most extreme states, providing glimpses into conditions that might have existed in the early universe. The mystery of black holes lies at the very heart of our quest to understand the cosmos. From the event horizon to the singularity, from the groundbreaking images captured by the Event Horizon Telescope to the mind-bending implications of Hawking radiation, black holes continue to challenge and expand our knowledge of the universe. As we develop new technologies and theories, we get closer to unlocking the secrets of these enigmatic objects, shedding light not only on black holes, but also on the very nature of space, time, and existence itself. The study of black holes is not just about understanding one of the most intriguing aspects of astrophysics. It's about answering some of the deepest questions we have about the universe and our place within it. The future of humanity is a topic that stirs both excitement and fear, leaving us to wonder where we are headed as a species. Will we continue to evolve slowly over millions of years as nature intended? Or will technology and science dramatically speed up our transformation? With groundbreaking advancements in genetic engineering, artificial intelligence, and biotechnology, it's clear that our future could look drastically different from anything we've known before. For millions of years, evolution has shaped us, carefully refining our physical and mental traits in response to the world around us. But as we look to the future, we begin to realize that evolution may not be the slow and natural process it once was. Without the pressures of survival that once guided natural selection, we may see evolution slow down, yet it could still continue through random genetic changes. The way the world changes around us, such as the effects of climate change, might push us in new directions. Some scientists believe that future humans may become taller or leaner, while others worry that our brains might shrink as we rely more on technology for cognitive tasks. And with advancements in healthcare, it's possible that our lifespans could extend, bringing new possibilities and challenges for our evolution. But the biggest change could come from our own actions. Genetic engineering, the science of modifying an organism's DNA, could allow us to change humanity in ways we never thought possible. Technologies like CRISPR are already letting us edit genes with precision, opening the door to eliminating inherited diseases, enhancing human abilities, and even selecting traits like eye color or intelligence. The idea of designer babies has gone from science fiction to a real possibility. And while it could prevent suffering from genetic disorders, it also raises troubling ethical questions. Could this technology create a world divided between those who can afford genetic enhancements and those who cannot? The risks are not just about fairness, but about unintended consequences, such as reducing genetic diversity, which could leave us vulnerable to unforeseen challenges. Artificial intelligence is another force that could radically alter our future. AI is already reshaping how we work, learn, and interact, but its influence may go far beyond that. Imagine a world where our brains can connect directly to AI through neural interfaces, enhancing our abilities in ways we can't yet fully comprehend. As AI takes over more tasks, we might rely less on our natural intellect and more on machines. This could create a divide between those with access to enhanced abilities and those without, deepening societal inequalities. The possibility of merging humans with machines, turning us into cyborgs, or even uploading our consciousness into digital networks, raises profound questions about what it means to be human. As we explore these possibilities, we must also confront difficult ethical questions. Is it right to alter the very essence of what it means to be human? Genetic engineering, especially when it comes to choosing traits for future generations, raises concerns about whether we are playing God. If only a privileged few can afford these enhancements, we risk creating a world of genetic haves and have-nots, further dividing society. Similarly, as we merge with machines, we must ask whether we are losing something essential about our humanity. The potential for misuse is also alarming. To better understand what the future might hold, we can look at real-world examples and speculative scenarios. In 2018, the Chinese scientist He Jiankui made headlines by creating the first genetically edited babies using CRISPR. While the intent was to prevent HIV, the experiment sparked a global debate about the ethics of genetic modification. Similarly, the company Neuralink, founded by Elon Musk, is working on developing brain-machine interfaces that could one day allow us to enhance our cognitive abilities or even restore mobility to paralyzed individuals. These advancements are steps toward a future where the lines between human and machine blur, creating new opportunities and new challenges. Some futurists imagine a world where humanity evolves into multiple species, each shaped by genetic and technological enhancements. Others speculate that humans might adapt to life on other planets such as Mars, or even achieve digital immortality by uploading our minds into AI networks. As we move forward, it's crucial that we balance progress with responsibility. We must ensure that transformative technologies are used wisely and equitably, so that everyone has access to their benefits, not just a select few. Global cooperation will be key, as international regulations and ethical guidelines will be needed to navigate this new era. Preserving the diversity of our species, both genetically and culturally, will also be vital to our long-term survival and resilience. And perhaps most importantly, we must ensure that we do not lose sight of the humanity that makes us who we are as we push the boundaries of what's possible. The universe we see before us, filled with stars, galaxies, and vast stretches of space, is awe-inspiring. Yet modern science suggests that this is only a tiny piece of the bigger picture. What if there are other realms beyond our three-dimensional world, dimensions that we cannot see, touch, or even measure? Could these hidden dimensions hold the key to understanding the universe in ways we've never imagined? To begin, we need to understand what dimensions are and how they shape the universe around us. In everyday life, we experience three dimensions of space: length, width, and height, along with the dimension of time. These four dimensions make up the reality we know, but scientists have long wondered if there are more dimensions beyond these four, ones that are invisible and curled up so tightly that we can't detect them with our senses or instruments. The idea of extra dimensions isn't new. It goes back to the 19th century, when mathematicians first began imagining the possibility of spaces with more than three dimensions. This opened the door for future theories that challenged everything we thought we knew about the universe. String theory is one of the boldest ideas that suggests the universe might have more than just four dimensions. According to string theory, the building blocks of the universe aren't tiny particles, but rather vibrating strings of energy. To make the math work, string theory proposes that there are up to 10 spatial dimensions that are hidden from us because they are curled up on an incredibly small scale. In this view, the way these strings vibrate in these higher dimensions determines the properties of particles, like mass and charge. M-theory, a more advanced version of string theory, goes even further, suggesting that the universe has 11 dimensions, and that our observable world might be a three-dimensional brain floating in a larger, higher dimensional space. Although it's difficult to directly observe these extra dimensions, there are signs in the universe that hint they might exist. For example, the cosmic microwave background, the faint glow left over from the Big Bang, shows strange irregularities that some scientists believe could be the result of interactions with higher dimensions. One of these anomalies is a cold spot in the CMB, which some theorize could be caused by a collision with another universe or the influence of extra dimensions. Similarly, gravitational waves, ripples in space-time caused by massive cosmic events, could provide more clues about higher dimensions. If these dimensions exist, they might change the way gravitational waves travel. Dark matter and dark energy, two of the biggest mysteries in the universe, may also be connected to these hidden dimensions, possibly offering an explanation for why the universe is expanding at an accelerating rate. String theory and M theory offer the most compelling frameworks for understanding higher dimensions. In string theory, the additional dimensions are thought to be compactified into complex shapes known as Calabi-Yau manifolds. These shapes allow for 6 extra spatial dimensions to coexist alongside the 3 we experience. The vibrations in these compactified dimensions influence the particles we see in our universe, affecting everything from the strength of gravity to the behavior of atoms. M theory extends this idea even further, suggesting that the entire universe might be a brain floating in a higher dimensional space. If multiple brains collide, it could explain phenomena like the Big Bang, potentially giving us insight into the cyclical nature of the universe. Despite the challenges in detecting extra dimensions, scientists are using advanced experiments to look for evidence. The Large Hadron Collider at CERN, for example, is smashing particles together at near light speeds in search of signs that could point to higher dimensions. By studying how particles behave and looking for tiny black holes, researchers hope to uncover the presence of extra dimensions. Similarly, precision measurements of gravity at small scales may reveal subtle deviations from what we expect, hinting at the existence of compactified dimensions that are hidden from view. The idea of higher dimensions also raises profound philosophical questions. If these dimensions exist, what does that mean for our understanding of reality? Could the 3 dimensions we experience be just a small part of a far more complex universe? Some scientists and philosophers speculate that extra dimensions could be portals to parallel universes or alternate realities, suggesting that our universe might not be unique. This challenges the way we think about space, time, and causality, and forces us to reconsider humanity's place in the grand scheme of the cosmos. Exploring the possibility of unseen dimensions is more than just a scientific pursuit. It is a journey into the heart of our understanding of the universe. As we search for evidence of these higher dimensions, we are also exploring the limits of human knowledge and our place in a universe that may be far more intricate and boundless than we ever dreamed. Though we are still far from fully understanding the nature of these dimensions, the very search for them reminds us of humanity's unrelenting curiosity and desire to uncover the mysteries of the cosmos. The universe we see is only a fraction of what could be out there, and the quest to uncover its hidden layers is a journey worth undertaking. The question of whether we have true free will, or whether our actions are determined by forces beyond our control, is one of the most fascinating and enduring debates in philosophy. Are we the ones in charge of our decisions? Or is everything we do already set in motion by things we can't even understand? Whether it's biology, our environment, or something more cosmic. This question gets to the very heart of who we are as human beings, shaping how we think about morality, justice, and responsibility. To begin, we must first define what free will and determinism really mean. Free will is the belief that we can make choices independently, without being forced or controlled by external factors. When we exercise free will, we feel that our decisions come from our own thoughts and intentions, and we believe that we could have chosen differently. Key ideas here include autonomy, the ability to make our own decisions, moral responsibility, the idea that we are accountable for our actions, and indeterminacy, the belief that not everything in life is determined and there is room for true choice. On the other hand, determinism is the idea that everything, including our actions, happens as a result of prior causes. Every event, every choice, is part of a chain reaction determined by the laws of nature, past conditions, and countless other influences. There are different kinds of determinism, like biological determinism, where our behavior is shaped by our genes, and environmental determinism, which suggests that our upbringing and surroundings shape who we are. The tension between free will and determinism raises deep questions. If everything is predetermined, can we be held responsible for what we do? But if we truly have free will, how does it fit with the seemingly perfect cause and effect order of the universe? The roots of this debate run deep in history, with major thinkers contributing their perspectives over the centuries. In ancient philosophy, Aristotle believed humans were rational beings, capable of making voluntary choices and taking responsibility for them. Epicurus, another Greek philosopher, introduced the idea that there might be room for free will in an otherwise deterministic universe, suggesting that random events at the atomic level allowed for genuine freedom. But determinism also had its champions, like Democritus, who believed that everything, including our behavior, could be explained by the movement of atoms, and the Stoic philosophers, such as Marcus Aurelius, who saw the world as unfolding according to a divine plan, urging people to accept their fate with peace. The tension between free will and divine omniscience was also a central issue in Christianity, with thinkers like Augustine and Aquinas struggling to reconcile human freedom with God's foreknowledge. Meanwhile, figures like John Calvin argued for predestination, suggesting that God had already decided the fate of every soul. As philosophy moved into the Enlightenment, thinkers like Baruch Spinoza and David Hume further explored these ideas, with Spinoza rejecting free will and Hume allowing for practical freedom within the constraints of causal influences. In recent years, advances in neuroscience have given us new insights into the question of free will. One major experiment, led by neuroscientist Benjamin Libet in the 1980s, measured brain activity before people became consciously aware of making decisions. The results showed that the brain was already preparing to act several hundred milliseconds before the person consciously decided to do so. This raises serious doubts about whether we truly have control over our actions. Some argue that this supports the idea that our choices are determined by unconscious brain processes, while others defend free will by saying that we still have the ability to veto or change the actions the brain initiates. Modern neuroscience continues to explore how much of our behavior is shaped by the subconscious, but it also acknowledges that conscious thought can influence complex decisions. Psychology, too, offers a powerful perspective on how external factors shape our choices. From classical conditioning, where behavior is shaped by external stimuli, to operant conditioning, which shows how reinforcement and punishment influence our actions, it becomes clear that our decisions are often not as free as we might think. Cognitive biases, such as the tendency to make decisions based on shortcuts or past experiences, further show how much our choices can be influenced by forces outside our awareness. Social psychology also highlights how authority figures and group dynamics shape behavior, as seen in the famous obedience experiments by Stanley Milgram. Many psychologists argue that much of what we think of as choice is really driven by unconscious motives or automatic responses. While free will and determinism seem to be at odds, some philosophers propose a middle ground known as compatibilism. Compatibilists argue that free will can coexist with determinism. They believe that freedom doesn't mean being free from all causes, but rather being able to act according to our desires and rational deliberations. In this view, we are free as long as our actions align with our intentions, even if those intentions are shaped by past experiences or external influences. Thinkers like Thomas Hobbes and John Stuart Mill argued that freedom comes from the ability to make decisions based on reasoning and internal motivations, not from being completely free of causation. The debate about free will and determinism has major implications for ethics, justice, and our understanding of human behavior. If determinism is true, can we still hold people accountable for their actions? Or should we focus on rehabilitation instead of punishment? On the other hand, if we have free will, how can we justify blaming people for actions they could have chosen differently? Our legal system assumes that people have free will and holds them responsible for their crimes. But recent discoveries in neuroscience and psychology raise questions about the fairness of this system, especially when behavior may be influenced by genetic or environmental factors. The belief in free will is also tied to human dignity and the pursuit of self-improvement, while determinism encourages a more humble view, reminding us of all the factors that shape who we are. Aging is something we all go through, yet it's a part of life that often leaves us with more questions than answers. Why do we age? Why do our bodies, which once worked so effortlessly, eventually lose their strength and resilience? These questions have fascinated people for centuries. Scientists, philosophers, and dreamers alike have tried to understand this complex process, not just because they want to know how our bodies change, but because aging speaks to deeper questions about our existence and what it means to live longer. We'll explore the biological mechanisms that contribute to aging. It's a complex process that involves molecular, cellular, and systemic changes, all of which lead to a gradual decline in our physical abilities. Telomeres, for example, are protective caps on our chromosomes that shorten every time our cells divide, ultimately limiting the number of times our cells can replicate. As our telomeres get shorter, our cells enter a state of senescence, which means they stop dividing and can start causing damage to our bodies. Meanwhile, oxidative stress, the damage caused by unstable molecules known as free radicals, continues to break down our cells over time. These changes, along with the decline in the function of our mitochondria, which are responsible for providing energy to our cells, contribute to the aging process. Scientists have also put forward various theories about aging. Some believe it's programmed into our biology, while others argue that it's the result of accumulated damage from environmental factors and metabolism. We'll look at the efforts being made to slow, stop, or even reverse aging. Technologies like CRISPR, a gene editing tool, offer hope for correcting the genetic mutations that contribute to aging. We'll also explore treatments like senolytics, which aim to remove damaged, aging cells from our bodies. Other methods, such as caloric restriction and fasting, have shown promise in animal studies for extending lifespan, while stem cell therapies are being used to repair damaged tissues and organs. Though these treatments are still in their early stages, they hold exciting potential for the future. However, with the possibility of extending life comes the need to consider the ethical and philosophical implications. What would it mean for us as humans if we could live forever? Would an infinite lifespan still hold meaning? Or would life lose its urgency and purpose? Some philosophers argue that it's our awareness of mortality that gives life its depth and creativity. If only a select few could afford life-extending technologies, would we be widening the gap between the rich and the poor? And if we lived longer, would we be putting more pressure on the environment and our resources? These are questions that we'll examine in the third chapter. Looking to nature, we see fascinating examples of organisms that seem to defy the normal aging process. Species like the tardigrade, the Greenland shark, and the naked mole rat have exceptional lifespans and unique biological traits that offer clues about how aging might be slowed or reversed in humans. These creatures may hold the key to understanding how we can better manage aging in ourselves. As technology advances, we're seeing exciting developments in precision medicine, where treatments could be personalized to our genetic makeup. Artificial intelligence and big data are helping researchers discover new drugs and therapies at a faster rate than ever before. By combining traditional wisdom with modern science, we may one day be able to find holistic ways to promote long, healthy lives. Aging isn't just about getting older. It's a journey that prompts us to ask important questions about who we are and what we value. The science of aging, along with the ethical challenges it raises, encourages us to reflect on life's purpose. While the quest to understand aging and extend life is ongoing, it reminds us to appreciate the time we have and to find meaning in our human experience. Emotions are at the very heart of what it means to be human. They shape the way we experience the world, guide our decisions, and affect how we relate to others. Whether it's the joy that fills us after an accomplishment, or the deep sadness we feel from a loss, emotions influence everything we do. But why do we have these feelings? Are they just the result of chemical reactions in our brains, or do they serve a deeper purpose that's essential to our survival and social lives? At their core, emotions are more than just random feelings. They have a purpose that helps us navigate life's challenges. The brain plays a central role in generating emotions, with areas like the amygdala responsible for fear and the prefrontal cortex helping us regulate them. Chemical messengers in the brain like dopamine, serotonin, and oxytocin also contribute to how we feel. Dopamine is linked to pleasure and reward, serotonin helps regulate our mood, and oxytocin, often called the love hormone, helps us bond with others. Emotions act as signals to guide our actions. Fear alerts us to danger, while happiness motivates us to pursue rewarding experiences. They also play a role in memory, making emotionally charged moments stand out and helping us learn from our past. While emotions are universal, the way they are expressed varies widely across cultures. For example, psychologist Paul Ekman identified 6 basic emotions: happiness, sadness, fear, anger, surprise, and disgust that are recognized worldwide through facial expressions. However, how these emotions are displayed can be shaped by cultural norms. In individualistic cultures, like those in the United States or Western Europe, people are often encouraged to express their emotions openly. In contrast, in collectivistic cultures like Japan or China, emotional expression is more restrained to maintain social harmony. Socialization plays a big part in this. Children learn from an early age how to express or suppress their emotions based on cultural expectations. Some cultures even have unique words for emotions that don't have a direct translation in other languages, such as Schadenfreude, the pleasure derived from someone else's misfortune in German, or Amae, the feeling of being lovingly cared for in Japanese. Emotions aren't just a personal experience, they also have evolutionary roots. Charles Darwin argued that emotions have evolved because they help us survive and thrive. Fear, for example, prepares us to fight or flee from danger, while emotions like love and affection promote bonding and cooperation, which are essential for raising children and maintaining strong social groups. Various theories help explain how emotions might have evolved. The James Lange theory suggests that emotions result from physiological responses, like feeling fear when our heart races in response to a threat. In contrast, the Cannon-Bard theory proposes that emotions and physical reactions happen at the same time, but independently. The Schachter-Singer theory emphasizes the role of our interpretation of situations in shaping emotions. These theories all suggest that emotions play crucial roles in helping us navigate the world and survive. In our interactions with others, emotions play a key role in shaping relationships and group dynamics. Emotions can spread from one person to another through a process known as emotional contagion, where we feel what others are feeling. For example, a leader's enthusiasm can inspire a team, while anxiety can spread quickly through a group. This ability to empathize with others is vital for resolving conflicts and building strong connections. Love, in particular, is one of the most powerful emotions, driving intimate bonds and the care of offspring. Whether romantic love or parental love, these emotions ensure that we form strong partnerships and protect our children, which is vital for the continuation of the species. Being able to understand and manage our emotions is what we call emotional intelligence. People with high emotional intelligence are more self-aware, able to regulate their emotions, and can empathize with others. These skills lead to better mental health, stronger relationships, and greater success in life. On the other hand, when emotions become overwhelming, they can lead to emotional challenges like anxiety, depression, or PTSD. These conditions show how dysregulated emotions can disrupt our lives and point to the importance of learning to manage our emotional health through therapy, mindfulness, and other methods. Infinity is a concept that stirs both wonder and confusion. It's a word that seems so simple but holds so much complexity. It challenges everything we think we know about the world, the universe, and even ourselves. In our daily lives, we are surrounded by things that are finite, measurable, and concrete. So the idea of something that never ends, something without limits, is hard to grasp. But infinity is everywhere, from the endless numbers in mathematics to the vast, ever-expanding universe above us. It's something we constantly wrestle with, trying to understand it, trying to find meaning in it. One of the most mind-bending aspects of infinity is the paradoxes it creates. These paradoxes force us to question the very nature of reality and logic. Take Hilbert's Hotel, for example. It's a thought experiment where a hotel has an infinite number of rooms, all occupied, yet it can still accommodate new guests. Even if an infinite number of guests show up, the hotel can rearrange the occupants in ways that make room for them. It's a concept that defies our understanding of space and size. Then there's Zeno's paradoxes, where ancient Greek philosopher Zeno suggested that motion is impossible because, to get anywhere, you would need to complete an infinite number of steps. Modern math, like calculus, shows us that these infinite steps can add up to something finite, but the idea of infinity still feels unreal. And then there's the infinite monkey theorem, which suggests that a monkey randomly pressing keys on a typewriter for an infinite amount of time would eventually type out the works of Shakespeare. While it seems impossible in real life, it highlights the strange possibilities that infinity presents. Mathematics gives us a way to define infinity in ways that make sense, even if they still seem strange. The work of mathematician Georg Cantor changed how we understand infinite sets. He showed that not all infinities are the same. For example, the set of natural numbers is countably infinite, meaning we can list all the numbers in a sequence. But the set of real numbers is uncountably infinite, meaning it's a much larger type of infinity. Through concepts like limits and calculus, we can even understand how infinite processes can result in finite outcomes. Beyond mathematics, infinity plays a huge role in the sciences, especially in physics and cosmology. The idea of infinite density in black holes, where gravity becomes so strong that it creates a singularity, pushes the boundaries of our understanding of the universe. In quantum mechanics, the concept of infinite energy densities introduces paradoxes that scientists are still trying to solve. And then there's the debate about whether the universe itself is infinite. While we know the observable universe has limits, theories like the multiverse suggest that there could be an infinite number of universes, each with its own rules. The idea that the universe might never end or that time itself could be infinite is both awe-inspiring and overwhelming. Philosophers and scientists alike struggle with these concepts, wondering about the nature of existence and our place in an infinite cosmos. Philosophically, infinity has been tied to the divine and the eternal. Many religious and spiritual traditions speak of an infinite God or an infinite reality that transcends our finite world. For some, the idea of infinity is comforting, an assurance of something eternal and unchanging. For others, it's unsettling, reminding us of our smallness in the face of a universe that seems beyond comprehension. The infinite nature of the universe also raises profound existential questions. If everything is infinite, does that make us and our lives insignificant? If there are infinite copies of Earth somewhere out there, does that change the meaning of our existence? The more we think about infinity, the more we are confronted with the limits of our own understanding and the mysteries of life. In modern technology, infinity is no longer just a philosophical or mathematical idea. It has practical applications. In computing, the concept of infinite processing steps, as seen in Turing machines, has laid the groundwork for everything from the internet to artificial intelligence. Our ability to deal with near infinite amounts of data is changing the way we live, work, and think. In virtual worlds and video games, technology simulates infinite possibilities, creating worlds within worlds, each with endless potential. The idea of infinity is becoming increasingly relevant as technology advances, forcing us to rethink what is possible. The universe is vast and ancient, stretching across billions of years and light years. As we look deeper into its endless expanse, we begin to wonder, what will happen to it in the end? Will it collapse into a fiery ball, slowly stretching out until it becomes a cold, empty void? Or will it undergo cycles of rebirth, constantly renewing itself? This question about the universe's fate stirs up emotions of awe and wonder, making us reflect on our place within it. To understand the universe's fate, we must first understand its origins and how it has evolved. Around 13.8 billion years ago, the universe was born from the Big Bang, a sudden and massive expansion from a single point, a singularity filled with infinite density. From that moment on, the universe has been expanding, with galaxies moving farther away from each other. This expansion continues today, and it plays a central role in shaping the future of the universe. The fact that the universe is still expanding is both thrilling and unsettling, as it leads us to wonder, how far can this expansion go? Will it ever stop? As we think about the future, several possibilities arise. One such scenario is the Big Crunch, where the universe's expansion eventually slows down, stops, and reverses. Gravitational forces would pull everything back together, causing stars, galaxies, and matter to collapse into a fiery singularity. It's a chilling thought, like the universe would eventually swallow itself, returning to the state it started from. But there's also the possibility of heat death, where the universe continues to expand forever, with matter and energy becoming so thin that everything grows cold and dark, unable to sustain life. This concept brings a sense of eternal stillness, where everything just fades away into nothingness. Another theory, the Big Rip, suggests that dark energy, the mysterious force pushing the universe apart, could get stronger over time, tearing apart galaxies, stars, and even atoms themselves, until the fabric of space itself unravels. And then there's the Big Bounce, a more hopeful idea. In this theory, after a big crunch, the universe could bounce back, expanding once more, starting the cycle of creation all over again. In all these scenarios, dark energy and dark matter play crucial roles. Together, they make up nearly 95% of the universe, yet we know so little about them. Dark energy, discovered in 1998, is thought to be responsible for the universe's accelerated expansion. It could either continue to push the universe apart, leading to a big rip, or lose its power, allowing gravity to take over and bring about a big crunch. Meanwhile, dark matter, the invisible substance that holds galaxies together, could also influence the universe's destiny, depending on how it interacts with other forces. The shape of the universe itself is another factor that determines its fate. Whether it's flat, open, or closed, this geometry affects how expansion will play out. Current data from missions like Planck and WMAP suggests that the universe is flat, which means that its expansion will slow but never stop. This supports ideas like heat death or the Big Rip, where the universe continues to stretch out into infinity. Each of these possibilities sparks a deep emotional response, making us feel small yet connected to something far greater than ourselves. The more we study the universe, the more we realize how little we understand. The observations from the WMAP and Planck missions, along with studies of distant supernovae, continue to refine our understanding of the universe's expansion and the forces that shape it. Yet, even with all this knowledge, the ultimate fate of the universe remains elusive. As we gaze up at the stars, we're reminded of our place in the cosmos, of how fragile our existence is, and how much more there is to learn. The thought of the universe's end raises deep philosophical questions about our own existence. If the universe will someday cease to be, what does that mean for us? How do we find meaning in the vastness of time, knowing that everything we know might eventually fade into oblivion? The cyclical nature of the Big Bounce and other theories challenge our traditional ideas of time, suggesting that the universe may be part of an endless cycle. Some even wonder if there are countless other universes, each with its own laws and destinies, making our universe just one chapter in an infinite cosmic story. Quantum entanglement is one of the most mind-boggling and fascinating phenomena in science, shaking the very foundations of how we understand the world. It challenges everything we thought we knew about reality, especially how we think about space, time, and connection. Albert Einstein, who struggled with this idea, famously called it spooky action at a distance because it seemed so impossible to accept. He believed that the universe operated in a much more predictable, orderly way, and the idea of particles communicating across space in an instant made no sense to him. But today, quantum entanglement is no longer a strange theory. It's a proven part of the universe, one that opens up so many new questions about the nature of everything. To understand this phenomenon, we first need to look at the world of quantum mechanics. Unlike the predictable world of classical physics, where things behave in a way we can measure and control, quantum mechanics is full of surprises. It tells us that particles like electrons don't have fixed properties until we measure them. In fact, until we observe them, they can be in multiple states at once, a concept called superposition. When two particles become entangled, their fates are linked. If you measure one particle, the other particle's state is instantly determined, no matter how far apart they are. It's as if the universe itself is connected in ways we can barely begin to understand, and that connection seems to defy the usual rules of time and space. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, once tried to argue against this idea. In 1935, they published a paper known as the EPR paradox, claiming that if quantum mechanics were right, it would mean that the universe was incomplete. They argued that the idea of particles influencing each other instantly couldn't possibly be true. It seemed to violate everything we knew about how the world works, especially Einstein's belief in locality, or the idea that nothing can affect something else faster than light can travel. Einstein didn't just dismiss quantum entanglement as a small detail. He saw it as something that threatened the very idea of a predictable, orderly universe. He called it spooky action at a distance because it just felt wrong to him. But despite Einstein's doubts, experiments began to push back against his beliefs. John Bell created a groundbreaking theory that would allow physicists to test the truth of quantum entanglement. His work led to the development of Bell's theorem, which showed that if quantum mechanics were right, entangled particles should show correlations that couldn't be explained by any local hidden variables or classical physics. Over the years, many experiments have confirmed Bell's predictions. Alain Aspect's experiments using entangled photons showed that the correlations between particles were stronger than any local realist theory could explain. Later, in 2015, new experiments closed any potential loopholes, providing the clearest evidence yet that quantum entanglement is real and doesn't just exist in the world of theory. The implications were mind-blowing. Local realism was wrong, and the universe really did work in a non-local, interconnected way. These findings challenge not only our understanding of physics, but also our understanding of reality itself. If entangled particles can communicate instantly, what does that mean for the nature of space and time? Some physicists suggest that space may not even be as fundamental as we once thought, and that entanglement could point to a deeper, hidden level of reality where everything is more connected than we realize. The very idea that our universe might not be governed by predictable cause and effect laws, but rather by probabilities and interconnectedness, invites us to reconsider everything we think we know about how the world works. But the mysteries don't end with philosophical ponderings. Quantum entanglement is not just a fascinating concept. It has real-world applications that are already starting to change the world. Quantum computing, for example, relies on entanglement to create powerful quantum bits, qubits, that can handle calculations far more complex and faster than classical computers. Quantum cryptography uses entanglement to create unbreakable encryption, ensuring that any attempt to intercept the communication would instantly be detected. And quantum teleportation, while still in its early stages, could one day allow us to transfer information securely across long distances in a way that was once unimaginable. Despite all the progress we've made, there's still so much we don't understand about quantum entanglement. Scientists are still trying to figure out exactly how it works and whether it can be harnessed on larger scales. There's also the question of how it might fit into a grand theory of everything, one that would unite quantum mechanics with Einstein's theory of general relativity. Some researchers even wonder whether entanglement might be key to understanding the strange phenomena of dark matter and dark energy, forces that seem to control the universe but remain hidden from us.